put my tie. Okay, so welcome to 377. The class is more or less full. A couple of seats here. So my name is Prashant. I will be the instructor for this class. Today is the first lecture. As you know, we are going to just do a brief introduction to operating systems, look at the syllabus, do a history lesson of operating systems, and that will be it for today. And then starting next week, we will basically start the actual lecture. Okay, so today's agenda is just to review what this class is about, why we need to look at operating systems as a course, and so on. Okay, so I will start with the introduction. So a few things to keep in mind. There is a course webpage where I will be posting all of the course materials. Okay. Today's lecture slides are already on there. We will also mirror everything, or hopefully everything that's on the course webpage on Moodle. So if you have used Moodle, you will see a 377 page for this class. And after every class, we will actually put up the course notes, the lecture slides. I'm recording the class, as I just said. I will try to also put the class recordings. Okay, class recordings are being done on a best effort basis. Okay, so if there's a technical glitch and I'm not able to capture a class, don't depend on it. Okay, by not coming to class, for instance. Right? So we will use Moodle for the course. We will basically have you upload all of your materials onto Moodle when you turn in assignments and so on. So all the assignments will come in electronically, and you will be handed back grades on or graded materials also on Moodle, okay, as you may have done for other classes. Okay, there are just to introduce you to the TA is Denny Wu. He's right here. He is going to be managing the discussion sections for the class as well as the labs. Okay? Of course, I am also here to help with lab questions and so on, but he is primarily going to be responsible for answering questions about the lab assignments and grading and so on. Okay? We also have a grading staff who will deal with the homeworks. He's not here today. Okay? So as far as the prereqs and books and all of that is concerned, you should have already taken 230. It's a prereq. Spire wouldn't have let you in if you hadn't. So I'm assuming that you have taken this class. That's a prereq for the course. We will have a couple of books that we will use. Okay, they are generally recommended. I'm not going to say you actually need to buy it. It's up to you. The main one is the Silberschatz book. It has lots of different editions. It spawns new editions every year. Okay? So not a whole lot different between them. So if you have a choice, buy the latest. If you want to buy a used copy and you get one edition behind, that's okay because it's not very different. Okay, if you have a choice, buy the Java version, okay, because the programming assignments will be in Java, but you can make do with the C version as well. Okay, here is a copy of it. This is actually one edition old, but as I said, any of these recent editions should be okay. There's another book, Modern Operating Systems by Tannenbaum, that I will use once in a while. I'll keep a copy on reserve in the library. You need to go refer to it. Okay, just go read it. So you don't need to buy two books. You can buy one. If you can make do without it, that's also fine. There'll be copies in the library. We'll be handing out course notes and whatnot as well. Okay. Course requirements, there will be homeworks and class exercises both in class and in the discussion section. And I'm expecting that you will actually ask a lot of questions. So there will be some small number of points for class participation. Collectively, homeworks, in-class exercises. There will be a quiz going out on Moodle every week, just so that you keep up with the course material. The quiz will go out on either Wednesday or Thursday, and it will close by Sunday. Okay, so if you don't keep up and you don't turn it in, you will not be able to turn it in late. This is just so that you keep up with the course. Okay? And if you miss a couple of quizzes, that's okay. Okay? I mean, it's a very small percentage of your total grade, but this is just to keep you in pace. Otherwise, you have other courses to take. You will basically only think about this class when time comes for exams and so on. But we would like you to keep up. Okay, so that's basically homeworks, Moodle quizzes, in-class exercises. Collectively, all of those things are 15%. Okay, so there are lots of small things here. 3 to 4 programming assignments, actually 3 real ones. There will be an initial lab that we will give out just so that you feel comfortable with Java programming and the exercises that you will have to do in class. Okay, the first lab doesn't actually count in terms of grading, but you do have to turn it in. The next 3 will actually count. Okay, those will be a substantial portion of the grade, as you see, approximately 15% each. Okay. Exams, there will be 2 midterms and a final, again around 40% of the grade. Okay, that's really what counts as far as grading is concerned. Okay, homeworks, class exercises, some programming assignment, 3 exams. Okay. Any questions on any of this stuff? Okay, there are some late policies spelled out on the syllabus, which is posted on the course webpage. Do take a look at it. Typically, very standard policies on you need to turn things in on time. You can get medical exemptions, but you have to document it and so on. We will, for lab assignments, we will allow you a total of 2 late days across all of the labs. Okay? So you can use it any way you want, but once you use up your late days, that's it. I mean, then any other late assignments will actually be penalized as per the late policy. Okay, so keep that in mind. There are policies spelled out on cheating as well. You have to actually look at that. Your first homework is to go into Moodle and basically check a box saying I read the policy and I agree to it. Okay, and we will put that out shortly. So as far as the labs are concerned, yes, go ahead.
The late days, is that one calendar day or the gap between each class?
No, late days are calendar days.
Okay.
Every day after the deadline for an assignment counts as a late day. Okay. Okay. So as far as the labs are concerned, we have accounts for you set up on the Ed Lab. I'm assuming that most of you will prefer not to use it. Okay. You will prefer to use your own machines to do your lab assignments. That is completely fine. The only thing we ask you is when you turn in your lab, okay, which you will do via Moodle, you should at least make sure that the lab compiles and works on an EdLab machine, because that is what the TA will use to grade. The TA will not be able to use your machine to make sure it works. So if you hard coded some path names and so on, it may not work on the EdLab. So all you need to do is make sure you write your code well enough so that it's going to run on some machine other than yours, specifically on the EdLab machines where your labs will be graded. Okay, fairly common sense policy. If we cannot run your lab assignment, we can't grade it. Okay, so you just need to make sure that even if you don't use the EdLab to do any of your assignments, make sure it runs before you submit. Okay, and it's Java, so it's pretty standard. It should be fairly straightforward to check. We will have a discussion section that is actually going to be used to deal with the lab assignments. There will be discussions on what a lab is about, how you should approach it, and so on and so forth. The discussion section will also elaborate on the lectures. Okay? We'll use the discussion to do exercises and build up on some of the concepts we cover in the lectures and so on. Okay? So you do have to go to the discussion section. Don't just assume you can come to lectures and get by and miss your discussion. They are an important part of the course. Okay? It's a 4-credit class, so the discussion is also something you should be attending. Okay? We will have office hours, both Danny and I. So you can come and ask questions, ask for help. My office hours, I typically have them right after class. This is just so that if you have a question that comes up in the lecture, you can come right afterwards and get them clarified. I understand that some of you may have another class right afterwards. So if you need to come see me some other time, you can always make an appointment. Okay? Denny's office hours will be on Tuesdays and Thursdays, okay? 11:30 to 12:30. Room is to be determined. 207. Okay. Okay, that's in this building. So basically, you will be able to see one of us on any day of the week. Okay? Monday through Thursday, Friday is the discussion section, so you can of course come and ask questions. Yeah, so there's plenty of help available should you choose to come talk to us, which we encourage you to do. Okay, so I already talked about the programming assignments, 45% of the grade, in class exams 40%. Yeah, are there any questions about the syllabus? Okay, the grading will be done on a curve. Okay, so it's not absolute grading, which some of you may be assuming that's not the way we do it. We will basically normalize all the scores and grade accordingly. Any other questions? Okay, so as I mentioned, the labs you will be using Java. Okay, that's preferred for programming. You may work in groups of 2. Okay, not more than 2. You can of course turn things in individually. We encourage that you form groups because the first lab is going to be easy, but they will be more complex as we go along. Okay, so you're better off finding a team, forming a team, finding a partner to work with, and we encourage that you do that early rather than later. Okay, because then you may find it difficult to find someone to work with. Okay, so if you intend to take advantage of working in groups, go form your group as soon as possible. Okay, first lab will go out shortly. Yes,
should we each turn in an identical copy or just one?
Okay, question is should you all turn in identical copies or one? We will spell all of that out very clearly, but typically what you do is you turn it in once. Okay, and then you will have README files that you will turn in that will say who your lab partner is. You'll have designs that you spell out and all that. So when the labs go out, we will actually tell you what we are expecting. We'll come back, how you need to turn it in and all of that stuff. Okay, but yes, you will do it once. You don't need to turn in identical copies. Okay. Other questions about the lab? Okay, so as I said, the first homework is to actually go read this policy on doing your own work and plagiarism and checking a box that you read it and you agree to. Okay, you will not be getting any grades back for any of the other work until you actually submit this homework. Okay? It's a fairly trivial thing, but we do want you to read it and understand clearly what we are expecting. Essentially, your work should be your own. Homeworks you can discuss but not borrow, and you should of course not lend your work to others and so on. Okay? So straightforward policy, but there are often some confusion arises later on, so I don't want someone to say you didn't realize what was expected and not. Okay, so keep that in mind, and we'll hand out the first lab shortly. Okay. The other thing to keep in mind is the increasing number of device distractions in class, so I'm basically going to enforce a simple policy of not allowing any devices to be used in class. Okay, no phones, no texting, no laptops, no tablets, no Facebook, no email. There's no attendance. If you like to do other things over coming to class, feel free. I'm not actually taking any attendance, but if you come here, I think I expect that you listen to what's going on and not distract yourself and others who sit around. Because more than you, that 4 other people are looking at what you're doing and then get distracted as well. So I'm just going to enforce the simple policy of not having any of these devices. Okay, feel free to take notes on paper. Okay, still quite a useful thing to do. I will put up the course notes before class so you can print and bring the class slides, scribble on them. All of that is fine. Okay, so keep this in mind. There will be occasional violations, and then we will have to deal with them accordingly. Okay, if you bring a phone, turn off the ringer, which I haven't done myself, because they do tend to go off once in a while and cause other distractions. All right. Okay. So that's the syllabus, all the course policies. So for the rest of the class, it's going to be shorter than usual class today. We are going to do a quick overview of the course itself, meaning the topics and so on, and also do a history of operating systems. Okay. But before we start, let me sort of ask, what prompted most of you to take this class. Okay, maybe it was required for your plan that you've chosen. Maybe there were some other things that interested you. So I want to hear a few people speak up, saying why have you taken this class? What do you expect to get out of it? Okay, so I have some sense of what your expectations are as well. I've made our expectations clear in terms of grading and all of that. So who's here because it was just required and you didn't think too much of taking this class or not taking it? Come on, some of you must have said I need to take 377. Okay, who has actually played with Linux or Linux kernels and have deep fascination of this topic and have taken it for that purpose? Okay, some small number. Any other reason? Instructor is too easy. This is the class to take because I don't want to work too hard. Anything else? Yes.
I need 2 500 level comp sci courses, and this is a requirement for most of the good 500 level courses.
Okay, it's a prereq, so I better take it. Otherwise, I can't do more advanced coursework. That's a fine reason. Any other? I want to learn about operating systems. Anyone? Okay, so you feel free to let me know if you don't want to speak up. I would like to get your sense of what you're expecting from this class as well, so that we all have a good semester. Okay. This is the course outline. Broadly speaking, the first couple of classes will actually be introductory. They're not on this topic. There will be a quick revision of architecture. Some of this material is supposed to be part of 230, but often depending on the instructor, some of it is not covered. Clearly, to learn about operating system, you need to know what your machine contains, what the hardware looks like, because the OS is the interface to the hardware. So the very first thing we do starting next week is to start with an overview of computer architecture concepts. Okay? What is in the machine and how does what, then once you know that, it makes sense to start learning about how those hardware resources are managed by the operating system. Okay, so some introductory material which is not listed here, but once we get past it, the first major chunk of the course is going to be processes and threads. Okay, so we learn about what's a process. You probably know about what's a thread from 230, I'm assuming, and probably know about what a process is as well. Our goals here are to understand how an operating system manages threads and processes, not just what they are, but what the OS needs to do to manage them. Okay, so we learn about that. We learn about things like CPU scheduling and concurrency as far as the OS is concerned. Okay. So that's the first quarter of the course. The next piece is going to be on memory management. How the operating system manages the RAM on your machine, how is that arbitrated, how do you allocate it to processes, threads, and so on. Okay, fair bit of material there. The next quarter of the course is going to be I/O devices, and we will basically focus on one key I/O device, namely the disk, and look at storage and file systems. How does the OS manage disk space? How does it manage files? And we'll use disks as a proxy for how all of I/O is handled. Yeah, so that's just an example of one I/O device, but the concepts are similar. So we'll start with storage and file systems, and then we look at I/O devices in more general. Okay. Last component of the course is on distributed systems. This is basically the networking side of your machine. What does the OS need to do to network your machine? How do applications access things on the network and so on? Okay. So 4 major pieces, and the distributed systems class leads to more advanced topics that we will not cover here, but they are covered in other topics. Okay. That's fairly the structure of what is in the book as well. Okay. The first piece is on, first few chapters are on processes and threads, then memory management, I/O devices, file system, storage, and networking and distributed systems. Next question.
Do we have recommended readings listed out on Google?
Okay, will there be recommended reading? Typically, I will point out the chapter that we are on, as well as some sections, and those are assigned readings. So it would be good if you actually look at the book and read those topics before you come. So we will do our job and give those out. Okay? So if you want to keep up with class, do read it. If you haven't read it before, do read it afterwards so you know what's going on. Okay? Or you can always stop me, ask questions at any point. Okay? We are not in a hurry to cover every single bit about operating systems. Better that you learn some topics well rather than cover a lot of topics and not get anything out at all. Okay, so the more questions you ask, the better it will be for both you and everyone else. Okay, so never hesitate to stop me, ask questions. Always happy to revisit something and teach it again if necessary. Okay? Yes, there will be assigned readings, but yes, you can also use the class or the discussion to get into more depth. Okay? So with all of that, let's do a quick run through what's an operating system and then do some sort of a history lesson. Okay, so what is an OS? The definition would vary depending on who you ask and how you look at it. Okay? But essentially, there are two ways to think about it. Okay? Basically, it is the piece of software that sits between the hardware and the user. Okay? You have your machine, that's a piece of hardware. The OS basically runs on that hardware and provides you an easier to use, more convenient interface. Okay? So you, the user, or your applications don't have to deal with the complexities of the underlying hardware. When you create a file, you don't actually have to deal with where on your disk that file is stored. The OS takes care of that for you. Okay? You don't even have to tell the OS or decide a priori how large that file is going to be. Okay? The OS takes care of managing that disk space for you. File can grow over time, it can shrink and so on. When you start a process, the same thing. Okay? When you start an application up, it starts up as a process. Okay? You don't tell the OS it needs so much memory and it needs all these resources. The OS figures that out. Okay? So basically, the operating system is hiding some of the complexities of the underlying machine from you. So essentially, it provides a virtual machine abstraction. So you get a logical view of what your machine is. That it has some disk and where you can create files. It has some memory where your processes may be resident. It has a CPU where your processes run. But you don't actually deal with the complexities of how to allocate any of these resources to your applications or processes. The OS is going to do that. Okay, so it is an important interface, system level interface that sits between the user and the hardware. Okay? Provides a more convenient abstraction for the user. It makes it easy to use. Okay, it may or may not include the graphical user interface depending on the exact definition of the OS, but the interface, the graphical interface, makes it even more easy to deal with processes, applications, files, and so on. Okay? So that's a definition of operating system that we will use. Okay? So also the other thing to keep in mind is from an application programmer standpoint, the OS also makes it easier to write program. Okay? You don't actually have to specify how to allocate memory, which registers to use, all of that. The compiler, the runtime, and the OS will deal with all of those issues for you. Okay? So that's one definition. So there is, of course, all sorts of other definitions where the boundary of what is an OS and what are middleware that sit on the OS is blurred. At one point, Microsoft thought that Internet Explorer was part of the operating system. Okay? And depending on what, if you think about Chrome OS and all of these new things that are coming up, is a browser application or is it part of the OS? It depends on what exactly the goals of that system are, depend on where you put some of this functionality. Okay? So you'll see different definitions. The one that we will use for this course is here. Okay? So it's basically easier to use, more convenient virtual machine abstraction that is provided to the user. It is the piece of software that sits between the user and the machine, deals with the underlying details of managing the hardware resources. Okay, so here is a picture that shows exactly what I just said. That's your hardware. These are applications and the user interacts with the machine through its application. The OS is the one that is sitting in between. Okay, so it hides a lot of the architectural details from the processes and the OS. Okay, it provides the illusion of a bigger, faster, more reliable machine. Okay? As we go along, we will see that OS provides some convenient abstraction. So you may have, let's say, 4 GB of main memory on your machine, on your laptop. Okay? But when you start up processes, the OS doesn't actually enforce that hard restriction. The total size of applications that may be running may exceed the size of memory you have. Okay? So you are not limited by some of the hardware restriction that your OS may impose. Okay? You don't actually have to figure out, I have 2 cores, so I should only start so many processes. Okay? You can start as many processes as you want. The OS takes care of how they run on the CPU and so on. Okay? So a lot of these details are hidden from you and you get more convenient abstraction. Okay? You can also think of the OS as a resource manager. Yes, an entity that arbitrates access to resources. Okay, so it basically allocates resources to applications, to users, and in doing so, there is going to be some overhead. Not all of this will come for free. Okay, the OS has its own runtime overhead. Okay, so those are the taxes we will pay to get all of those benefits. So what we are interested in learning in this course is what are the right ways to design this operating system, okay, or the kernel. Okay. What design decisions make sense, what trade-offs are available to you as, let's say, an OS designer, and how do you make the right choice. You'll often see that there is no one answer to some of the design decisions. There are many ways to design an OS. Okay. Some may be appropriate for certain scenarios and other may be appropriate for others. Okay, so there is no one way. Okay, so how do you make the right choices? Okay. These lessons are not unique to operating systems alone. When you design any software system, you will see that you are faced with many choices. Do you make it faster and simpler, or do you add more functionality which adds overhead? And a very common trade-off that you have to make. Okay, if you make it faster, your users and or applications may be happy. They get to basically execute, the applications execute faster, the user feels the machine is responsive and fast, but then you may not provide enough functionality. As you add more code, more functions, there is an overhead you have to pay. Okay, what's the right trade-off? Should you pack so much functionality that the machine becomes slow, then the users are not happy, but you have a very rich set of functions. These are often issues that system designers, not just OS designers, any system designers might grapple with. Okay, so one of the other orthogonal goals of this course is to teach you how to design large software systems. Typically, the OS is one of the largest pieces of software you may have interacted with on your machine. Okay? I mean, Windows has tens of millions of lines of code. Okay, so it's fairly complex, very complex piece of software, many decisions to be made. So how do you design an OS well? Okay, these lessons you can apply to how do you design any software system well. Okay, so lessons here are more universal than just the topic. So that's one of the other goals of this course, is to teach you good software systems design in terms of making the right trade-offs and even knowing that there are trade-offs to begin with. Okay? Any questions about this? Okay, so now operating systems have been around for now almost more than 40 years. They were first designed in the 60s, yes, actually 50 years. They continue to evolve with the time. Okay, there are new demands, there are new hardware abstractions, there are new devices. So OSs must evolve, okay, to address these new needs. So 10 years ago, nobody talked about phone operating systems. The phones actually, you never even thought they had an OS. Now you have a whole slew of phone operating systems, iOS, Android, and there are a whole bunch of new ones as well. Okay. So, and then there are many other tiny devices that also run operating systems. At the other end of the spectrum, you have very large server farms called data centers, or you may have heard of the term cloud computing. There are very large collections of servers that sit somewhere remotely that you can access services. Okay. Operating systems must also deal with this very large setup. Okay. So it's not just the thing that runs on your machine. It may soon be the thing that runs on your watch. It's certainly the thing that runs on your tablet and phones. and they also run on server. Okay, so there is a variety of hardware devices that an OS must manage. Okay, and clearly you don't have to do the same thing on each of these devices. The way you manage resources on a phone or a small device may not be the same way you have managed resources on a server farm or a data center, okay, or on the cloud. Okay. So operating systems must evolve to meet each of these hardware needs. Okay. So the field is continuing to grow. The number of OS platforms are also continuing to grow. There are probably dozens and dozens of Linux distributions alone, okay, for anything from embedded devices to large cloud platforms. So we'll see some of these newer topics, web, grid, cloud, maybe later on in this class. Okay, once we know the basics, we can then look at how do you apply this to new environments that are emerging, as well as hardware that's emerging. Okay, so multi-core operating systems, another active area of research. Okay, phones already have going quad core. Okay, some servers have 64 cores. How do you manage them as an operating system? What are the right design decisions to make? Okay, operating systems must evolve as hardware evolves. Okay, when they were designed 20 years ago, nobody thought about designing kernels that will manage 64 cores. And now that they are here, you have to think about this issue as well. Okay. So that's something we'll look at as we go along. There's also a vibrant open source community built around operating system led by Linux and BSD and so on. Okay, so that's another area where there are lots of users. They contribute to the development of operating system. But as a user, you can actually go and, not user, as a student of operating system rather, you can go and actually look at real kernel code. It's all open source, and you can get a feel for how operating systems are designed. So it's fairly easy to use as an educational and research platform. Now in this class, we are not going to do any Linux kernel work. There are more advanced courses that we offer here where we do that. But if you're curious, it's an avenue that's open to you. Okay. Okay. So some more definitions / background. So the operating systems provides a number of services that we will look at as we go along. There's the file system or the file service, there's the memory management, there's the networking service, there's time sharing as a service, and so on. Some of these terms don't mean anything to you, don't worry about it, we will define them carefully and look at them as we go along. But the way operating systems are designed is there is a kernel and it provides a number of services. And what we like to do is take a look at each of this service, see how to design it, what it does for the user, what kinds of trade-offs exist when you design it, and so on. Okay? So that's one way to look at the course. The other way is to think of operating system as a coordinator or a resource manager. I just mentioned this already. This is also going to be an important aspect. Given a hardware resource and competing demands for that hardware resource, what kinds of policies make sense? Okay, from a fairness standpoint, from a responsiveness standpoint, and so on. Okay, so we'll look at a number of resource management policies, starting with CPU scheduling. We'll look at I/O scheduling, we'll look at memory management. All of those are resource management policies. Okay, if you have 10 processes and 2 cores, okay, how do you decide which process gets to run on which core and for how long? Okay, the OS has to make this decision. That's a resource management decision. What policies make sense? Okay, as we go along, we'll look at all of these resource management policies. That's another way to think about operating systems. Okay? So basic goal of this course is to understand how to design operating systems so that it's convenient to use, so the abstractions are easy to use and also efficient to use. Okay? Convenience is really a software engineering problem. Okay? What does the interface look like? What abstractions to provide? That's more of a software engineering problem, but we are going to look at it here. And efficiency is a systems and an engineering problem. Okay? That's where the trade-offs come in. Okay? How do you design it so that it is fast yet functional? Okay? So these are basically, so we'll want to study operating system design from this standpoint. Okay? What are the right abstractions? How do you make them efficient? How do you make them functional? Okay, so multiple goals. We'll see that there are often conflicts. Okay, maybe you have to decide between convenience and efficiency in some cases. Where do you draw the boundary? Okay, so these are things we look at. Okay, so I think I mentioned most of this already. So we'll look at a number of trade-offs between performance and convenience, performance and functionality, what's in the hardware and what's in the software. Okay, that's an important issue as well, because the operating system has to provide certain abstraction and deal with the hardware. You can even ask what should the OS do and what should the hardware do. The more mechanism the hardware provides, we'll see it's easier to implement certain functionality in the operating system. But if you have more bare bone CPUs, okay, the OS has to do more because the hardware does less for you. Okay. So as a hardware designer as well, although the course here is not about hardware design or computer architecture, you have to think about what should you put in the hardware, okay, and what is best left to the operating system. Okay, so that boundary between software and hardware is also an important one. And depending on where you draw the line, what goes in the hardware, what goes in the OS design will become more complex or more easy. Okay? Some things we'll talk about starting in 2 classes when we do process management. Okay, so we talked about all of this. Okay, so here are some things that you ought to know. Okay, some architectural details. I'm going to do a review of that. Okay, so C, C++, you don't really need to know. Okay, because we switched the course to Java. So we will not assume you know too much C, C++. But if you know some of that, it may be good as we talk about memory management and pointers and so on. It will be useful, not required. Okay, so some of these other things are being taught a little bit in 230, like concurrency and threads and so on. We'll try to build on those topics. Because I'm not assuming that you are an expert on threads or concurrency, but I'm assuming you have some exposure to that from 230. That is reasonable. Heard of threads, concurrency, and so on, right? So we'll build on that and we'll look at it from the operating system standpoint. This I think we are going to look at as we go along. Okay? Server architectures, distributed computing, file systems, and so on. Okay, so that's a very quick overview, essentially a definition of an operating system and various ways to think about what an OS does for you, the user, and your application. Now we are going to do a quick history lesson. Okay, so how operating systems have evolved over the ages. Okay. So you have to actually look at this history lesson starting in the 60s. Okay, so basically the very early machines that were available, computers rather, were mainframes. Costs a lot of money. In those days, they cost millions of dollars. Okay, they are very large. Okay, some of them are actually the size of this room. You can think of a machine that's as big as the size of this room. That's a single machine. That's how mainframes were built. Okay? So they were very expensive as compared to hiring programmers. Because so the way to think about it is the hardware was expensive as compared to people. Okay? Hiring a programmer in those days may have cost a few $1,000s, but by buying a machine, cost you millions of dollars. Okay? So, and the operating system that ran on this machine also did very little. Okay, it allowed one user to use the machine at any given time. It allowed only one program or process to run on that machine at any given time. Okay, so you buy $1 million piece of equipment, it runs one thing and one thing only, and more only one user can access it at any given time. But that's the way things were. Okay, so the OS didn't do very much in terms of resource management. It did not even allow you to exploit any parallelism. Okay? Either it did computation where the program that you wanted to run ran on the CPU, or it did I/O. It spat out the output of your program. Okay? So very bare bones operating system functionality on a very expensive piece of hardware. Okay, and debugging was essentially a nightmare. You had to actually sit on the console and run the program, look at the outputs, and that didn't quite do what I wanted it to do. Scratch your head, figure out what happened, and then reload the program, run it again. Very painful process. Right? Mostly because the software didn't do very much. It essentially loaded the program, ran it, produced some output. That's all it would do. It was essentially batch processing. Okay? Programs ran in batches. So then OS designers started saying, why not make the OS a little more functional? As hardware is expensive, uh, you should make better use of the hardware. So how do you do this? Okay? So why not let multiple users, okay, use the machine? Okay, so what you could do then is rather than having a single process or application run, you could feed a batch of programs. Okay? The OS would still load one program at a time, but then while it was loading one, you could running one, you could start loading the other. So you could use a little bit of parallelism, but have a stream of applications being loaded, run, and produce output. Okay? So you submit jobs, and then there was a scheduler that would schedule these jobs and start running them one after another. So the time for which your expensive piece of hardware was idle, because the user is just loading something or so on, was reducing. You could basically get more throughput from your expensive machine. Okay? Could make better use of that machine. So it's sitting idle for less time. Okay? So it's more efficient use of the machine. Okay, so this required the OS to do a simple form of batch scheduling, okay, where you could load programs in batches, they would run, they would produce output and so on. Okay, so this brought in the era of batch processing, still very primitive operating system. Okay, no interactivity, no multiple users, just batch processing. Okay. Third innovation was, why not basically let I/O and computation overlap? Because this is true even today. Okay. The OS has to manage a CPU, it also has to manage I/O devices. There is no reason it should only do either CPU or I/O. You could do both at the same time. Some processes could be doing I/O whilst others are actually using the CPU. Makes even better use of your hardware. Okay? So essentially you could allow the CPU to execute while some other program is doing I/O. Okay? By overlapping computation and I/O, you can make better use of those. Today's operating systems still do this. Okay? When your one process starts doing I/O, it starts running another process on the CPU, so that other process can make progress while the first one is doing slow I/O. Okay? So overlapping computation and I/O is an important design principle. Okay? Appeared about 30 years ago, okay, but still with us today. We'll look at how to do this better when we come to some of the main technical topics. But from a history standpoint, this was sort of a natural path in evolution. Okay, saying we have multiple resources, let's use them in parallel, okay, rather than using only one resource at a time. So you go from one user using one machine to users feeding batches of programs, okay, to using multiple resources concurrently on the machine. Okay? Gets you much better efficiency. Okay. Next point in the evolution was essentially multi-programming. Okay, so going from uni-programming to multi-programming, where you have the ability to run multiple processes simultaneously. Okay, going from one process at a time to having multiple processes. So this you don't even think of today. Okay, typically when you look at what's running on your machine, there may be dozens of processes running. Okay, that's multi-program. Uni-programming is where you have only one process running in on your machine at any given time. Okay. Multi-programming says multiple processes loaded and they are all running. If you have a single core, only one of them may be actually executing. Okay. But there are more than one resident, so you can switch between them quickly. Okay. One starts doing I/O, you can run another one. Okay. So you run one job until it starts doing I/O. Once that starts doing I/O, the other one that's already resident gets to run and so on. So you can cycle between them. They all make better progress. Okay. So multi-programming is also somewhat tied to multiple users using the machine at the same time. Okay. Most modern operating systems will allow multiple users to log in into a single machine at the same time and use the machine concurrently. Okay, this may not happen on your laptop, which you and you alone use most of the time, but most servers will allow you to have multiple users logged in and use the machine. Each one can have their own applications, processes running. Okay? So multi-programming is required in order for you to let multiple users use that machine. So each user can run their own set of processes. Okay? And the OS has to deal with multi-programming. Okay? So which job to run, that's the scheduling problem. how to decide how much memory to give to each process. That's memory management. How do you decide which one to resume when the CPU is available? That's also a scheduling problem. So now the complexity of what the OS has to do keeps rising as you add more function. If you want to overlap ion computation, your OS has to be richer. Okay, if you want to allow multiple programs to run, it has to do better resource management. Okay. So the complexity of operating systems grew from the 60s to the 70s to the 80s, and there were ever more ambitious OS projects that try to build richer, more functional operating system. Okay. I don't know if anyone of you heard about Multics. Okay, this was the one big failure of an operating system design project in the 60s. Okay. This was an operating system that GE, the company, and MIT decided to build. It was supposed to be a grand vision of building a rich, highly functional operating system that would do everything, okay, other than the laundry. Okay, so it was basically a project that ran for many, many, many years and then eventually was abandoned. Okay, I mean, it was released, but abandoned in the sense users didn't use it because it was very hard to use, very slow, very complex. Okay, because they made the wrong design choices. They tried to pack too much in. Okay, they didn't think of what is the common case. They tried to cover every corner case and made the OS so complicated and so riddled with bugs, because larger the piece of software, the more bugs it tends to have, and it was not usable. Okay? So not usable, then people will not want to use it. Okay? This you see over the years. Okay? So you may have heard of Vista and having growing pains, and Vista came on Windows like this, and all these similar problems. It was very complex, ran very slow. People didn't want to switch. They were happy with what they had already. The same was true here. Okay, so that was actually a good learning experience. A good failure from a software engineering standpoint, very poor design choices, okay? But nevertheless had ambitious goal. Okay? Now what came out of this failure was Unix. Okay? In the late sort of in 1969, some of the designers who were affiliated with this project said that this is the wrong way to do operating system. Let's go the other way. Let's shoot for simplicity. Let's build something simple, that's fast and does the job. It doesn't give you too much functionality, but we let users and our application designers build on top. So basically Unix took the lessons from Multics, or rather the failures of Multics, and basically went the other way. Okay, so the original designers of Unix, Kerning and Ritchie and a whole bunch of others from Bell Labs, Unix came out of Bell Labs, said the way to do it is to go simple. We'll build something basic. It'll run, do its job. It won't have a whole lot of features, but because it is efficient, fast, gets the job done, hopefully users will want to use it. Okay? And as you know, Unix was actually a big success. It is basically exists in some flavor or the other even today, okay? Maybe 40 years later. Okay? So that tells you from a software engineering standpoint what might have worked and what did not work. Okay? Now those were lessons from the 60s, but those mistakes have continued to be repeated. Every once in a while you see a major revamp of the OS and some wrong design decisions are made and users are not happy, saying this is far too complex. I think now there are, if you read the Popular Plus, you will see grumblings about Windows 8, saying they changed the interface, things were working fine, now I have to learn new things, it doesn't quite work for me and so on. Okay, some people like it, but many hate it. Okay, whether they have the right design choices, okay, we don't know. Microsoft wants to put back some of the old interfaces, so that may tell you something. Okay? So you have to be careful in terms of what design decisions you make. Or you want to keep your users happy as an OS designer. Okay, they look for efficiency, they look for responsiveness, they look for usability. Yeah, often you make the wrong decision and it hurts the popularity of that OS. Okay. So that's the way to sort of, not the way, those are some of the lessons to learn from what to put in the OS, the complexity versus simplicity argument. It's an important one for any software design. So basically, I talked about Unix already. So from the failure of Multics, you basically had Unix come out, and they basically built by only 3 guys in the very beginning. Okay, so you can think of Multics had an army of OS designers who are associated with the project. Unix was built by essentially 3 of those guys who learned the right lessons. Okay? Very different design philosophy. Okay? And still we have Unix with us, and Multics is long forgotten, only in textbooks now. Okay? So that's basically Unix. And if you now trace the evolution into the 80s and 90s, what you see is that hardware has progressively gotten cheaper. Okay? From $1 million mainframe, now you could buy a Pro PC for a few $1,000s. Several orders of magnitude reduction in cost. Okay? Hiring programmers didn't get cheaper. If anything, it got more expensive. So now you have to rethink your design trade-offs. If everyone has a PC or has their own machine, but programmers are still expensive, then the OS should be designed so as to make the more expensive part more efficient. So now you want to not think of how to make the hardware efficient, which was what happened in the mainframe days, but how do you make people do things more efficiently? If people get more done, you have overall better productivity. Yeah, because people are the more expensive part of the equation. Yeah, so all of OS design basically has focused more on usability, starting with the 80s. Everyone could own a machine. Not everyone in those days, but every programmer, the company that they worked for could afford to give them a machine, and you have to make them productive because they are the more expensive, not the machine anymore. Okay, so that basically gave rise to Windows and early versions of Mac, which are a graphical user interface. Much better than sitting on a terminal window and typing command line stuff. Yeah, so you could get more work done just by having graphical user interfaces. So mice, keyboards, all these new GUIs were designed all in the 80s with the rise of PC-based operating systems as opposed to server-based operating systems. Different design trade-offs. Okay? Early versions of PC-based operating system made very similar design decisions as the early mainframe because it was meant for a single user. The first versions like DOS did not have multi-program. Later on they did. Okay, they did not do very much in terms of memory protection, okay, which of course gave rise to viruses and so on. Hackers had a field day saying I can now go in and put some malicious code and take over your machine and so on. Okay, later on, operating systems evolved and all of these features actually went back in, but not the early one. Okay, and then you had networking and file sharing and remote printing and all of these things came along. Okay. And this trend has only accelerated. If you look at the 1990s and 2000, okay, the price of hardware has continued to drop. And now, from few thousand, you can buy machines for a few $100s. The tablets cost a few $100s now. Okay, so hardware has become very cheap. Now, rather than having one machine per user, each user has multiple devices. Okay, you have a phone, which is really a mesh computer. You have a tablet. You may have access to a laptop. You may have computing embedded in things that you don't even think of them as computers anymore. So you have embedded computing where tiny microcontrollers may be embedded in your environment. Your car may have like 6 microcontrollers. Okay? It runs a small operating system. You don't think of your car as a computing device. Okay? But it actually has a fair bit of computational resources on it. Okay? You may have tiny sensors that have microcontrollers that are doing very specific things. You don't think of them as computing devices. Right? So here is one. So this is a pedometer, okay, that has a Bluetooth and a small screen. It measures how much you walk in a day. Okay? It has a tiny OS running on it. You can program it. Okay? You don't think of these devices as machines, okay? But they are. You have to design operating systems for these kinds of devices as well. Okay? So very different way of thinking about what OSs need to do. Multiple devices per person, very specific hardware designed to do one thing alone. What should the OS do? How should you design the programming environment and so on? Okay? So this has given rise to a whole new set of requirements. There is real-time operating systems. Okay? These are operating systems that run on really mission critical stuff. Okay? Airplane, nuclear reactors, where things you cannot afford to have things go wrong. Okay? And that may be catastrophic. How do you design an operating system to manage a nuclear reactor? Okay? That's the domain of real-time operating system. We're not going to look at that here, but there is an entire body of work and products where you have the real-time kernels that are designed to do things with high reliability, to get things done on time and so on. Okay? There's parallel operating systems where the OS has to manage lots of, in this case, let's say cores. We have, as I said, 64 core machines. You need parallel operating system. Your distributed operating systems where the OS runs on a set of machines, okay? A cluster or a data center or a cloud. So this is basically how all of the operating system world, how it has evolved. Okay? So you have a broad spectrum of things that OS kernels are called upon to do. Okay? So there's increasing specialization as well. Okay, so this is just a chart that basically shows how hardware has gotten more capable, how the cost has dropped. I already mentioned this as we went along. Prices have continued to drop. Okay, this is also, and machines have gotten more powerful. This is an artifact of what's called Moore's law. Okay? I don't know if you covered Moore's law in 230. Anyone know Moore's law? 230, right? So just as a recap, Moore's law essentially says that every 18 months to 2 years, okay, your the number of transistors that you can put on a chip will basically double, okay, because of advances in technology. Okay. What has this got to do with computing? So you can think of things that get approximately twice as fast or twice as more powerful every 2 years. Okay, so if you have a 4-core machine that you can buy for a certain amount, a 4-core CPU, let's say, in 2 years you should be able to either buy a 4-core machine or 4-core CPU that's twice as fast, or have you twice as many cores. They're roughly the same thing. You can get more performance or more capacity, okay, because you have higher density of chips. So this trend has been with us for almost 30 years. The speeds have been doubling for every 2 years for the past 30 years. So that's almost exponential increase in capacity. Or if you keep for the same capacity, that's an exponential decrease in cost. If you want to keep the same performance, you have a chip that's 1/4 the size, so it costs much less. So Moore's law has had very profound implications on how hardware capacities have increased, how prices have dropped, and how operating systems have had to keep up with this trend. Okay. Now, the law is still valid, although there are some wrinkles in how you actually think about it. But it basically allows us, gives us a reference point thinking about how hardware has evolved and how operating systems have had to keep up. So here is some other examples, other domains, and you'll see that no other domain has had this type of technology improvement. If you look at transportation, okay, so basically you have gone from horse carriages to probably airplanes. Okay, so 10 miles an hour to 1,000 miles an hour over a period of 200 years. Okay? 2 orders of magnitude improvement for 200 years. Okay? This you will get in 10 years if you will go with Moore's law. Okay? So very dramatic change of improvement of technology. Communication, same thing. Okay? Communication also, because it's all run by electronics, has some form of Moore's law working for it. So you get more bandwidth for the same price, or you get cheaper bandwidth, etc. So you will see that networks become ever faster. Okay? You may not see this as an end user, okay? Because your phone company or your internet provider may not be passing on all of those benefits to you, but they are getting those benefits working for them. Their routers become faster, backbone networks become faster, and so on. Okay? So this is probably the only other analog, which is the field of communication, which has also benefited in the same. Okay? Computing and communication are intricately tied, so you basically get benefit of both faster networks, faster machines. Okay, but if you look at transportation and all of these other domains, you don't see this kind of technology improvement. Okay, so just to give you pictorially a graphical depiction. So if you think of what 10 orders of magnitude means, we can take a picture and start zooming out. Or another way to think about it is, if this is a chip, how small will it get? Okay, or basically, what is basically this area, how small will it get on a chip of the same size as you get technology improvement? Okay, so that's a picture. You basically have one order of magnitude improvement. Whatever was on the previous chip is basically this size in this new chip. Okay, so the chip is far more powerful, 10 times as more powerful. Okay. Here is something that's 100 times as powerful. So that picture is not shrunk to that. Okay, that's sort of, you can think of that as your new chip. Okay, here is 3 orders, 4 orders, 5, 6, 7, 8, 9 orders. Okay, so that's a graphical way to think about what a chip was maybe 30 years ago, what you have now. Okay, whatever you could do 30 years ago on that chip will only take this much space on today's chips. Okay, sort of a computing chip. Okay, so Moore's law not quite running out of steam, but the problem that you're seeing with Moore's law is as you make chips more dense, they also need more power. Because you need to power those chips, and that is really where some of these problems have come up. And you can make the chips more denser, but supplying more and more power to these chips becomes a problem because chips do heat up. The power gets dissipated as heat. So eventually, if you pack too much, your chip is essentially going to melt. It won't run. So dealing with the power issues has actually caused some hurdles in this chip design. So now you see what thing called power-aware computing, where you don't necessarily make the chips run faster, but you make them more power efficient, okay, so that they don't consume ever more power. And this is true also of laptops. Because if you just kept up with Moore's law, your battery life would keep shrinking. If you have a chip that's twice as capable, it's going to consume twice as much power. Okay, that will basically halve your battery life. You don't want a very powerful laptop that runs out of battery in 10 minutes. Right? So that doesn't quite work. So the right design decision was not to pack more, but to make it more efficient. So you also have the right trade-off between computational power and the amount of energy your chip needs to run and battery life. Another of those design trade-offs that you have to live with. Okay, people expect faster things, but they don't want to give up on battery life. For mobile devices, at least. Okay, for servers, it's a completely different issue. Okay, if they're powered off the wall, it's less of an issue, although it is somewhat of an issue in data centers and so on. Okay. So now, basically, the new mantra, if you will, is not just pack more, but also make it more power efficient. Okay? This is, if you actually look at what Intel and AMD have been trying to do in recent years, they have not tried to make their chips ever more faster, but they are really focusing on making it more efficient because computing is becoming untethered and mobile. Mobile devices run on batteries, so making things faster and more power hungry is the wrong design decision. So they have been focusing on making their chips more efficient. ARM is this other company that always had a power efficient design. So it has really caught on in the world of smartphones. You see more ARM chips on your phones and tablets than you see Intel chips. For that very reason. Intel chips are more capable, also consume more power. And that has a bad implication on battery life and so on. So anyway, so I think there are all these design decisions. So the thing to take away, Moore's law is still valid, but there are wrinkles that come up because of energy efficiency issues and so on. But there are a host of new issues. Multiple cores, how do you deal with it? If you make memory more dense, how do you deal with the unreliability that you get out of this? Okay? As you go from traditional hard disks to solid state disks, how should the operating system scope up? And we will see when we look at IO devices, there are different design decisions to be made. This technology has completely changed. All of the optimizations that were valid for the past 30 years no longer apply because you don't need them anymore. How do you redesign your IO subsystem or disk subsystem to deal with it? Power, heat issues I already mentioned. There's battery life goes with that. Right? So there are many such trade-offs that we will look at in this course as we look at operating system design. So that's all we have for today actually. So I'm going to basically stop here. Feel free, come ask me questions and whatnot. If some of you, if haven't yet registered, need to talk to me, this is a good time. The course is almost full, can't accommodate too many other people. Okay.
Go.
One second.